A meter is any device built to accurately detect and display an electrical quantity in a form readable by a human being. Electrical meters are among the most important basic instruments. They let us see the invisible world of electricity. Usually, this readable form is a visual, a motion of a pointer on a scale, a series of lights arranged to form a bar graph, or some sort of display composed of numerical figures. In the analysis and testing of circuits, there are meters designed to accurately measure the basic quantities of voltage, current, and resistance. All three of these quantities are measured by multimeters. There are many other types of meters as well, but this tutorial primarily covers the design and operation of the basic three, which are incorporated in the common multimeter. Most modern meters are digital in design, meaning that their readable display is in the form of numerical digits. Older designs of meters are mechanical in nature, using some kind of pointing device to show the quantity of measurement. In either case, the principles applied in adapting a display unit to measure current, voltage, or resistance are the same. The display mechanism of a meter is often referred to as a movement, borrowing from its mechanical nature to move a pointer along a scale so that a measured value may be read. Though modern digital meters have no moving parts, the term movement may be applied to the same basic device performing the display function. The design of digital movements is beyond the scope of this chapter, but mechanical meter movement designs are very understandable. Most mechanical movements are based on the principle of electromagnetism, that electric current through a conductor produces a magnetic field perpendicular to the axis of electron flow. The greater the electric current, the stronger the magnetic field produced. The strength of the magnetism can be greatly increased by coiling the wire. This animation shows how current flowing through the coil of wire wrapped around a magnetic compass needle deflects it from the pointing north and south. Notice that if the electric current is reversed, the deflection is reversed as well. If the magnetic field formed by the conductor is allowed to interact with another magnetic field, a physical force will be generated between the two sources of fields. If one of these sources is free to move with respect to the other, it will do so as the current is conducted through the wire. The motion, usually against the resistance of a spring, being proportional to the strength of the current. The first meter movements built were known as galvanometers, and usually were designed with maximum sensitivity in mind. A very simple galvanometer may be made from a magnetized needle, such as the needle in a magnetic compass, positioned within a coil of wire carrying current. Current through the wire coil will produce a magnetic field which will deflect the needle from pointing in the direction of the Earth's magnetic field. Current meters like this were called tangent galvanometers. They were used in the 19th century to measure current. They had to be used on a tabletop. The coil had to be turned so the windings were parallel with the magnetic field lines between north and south. When current would flow through the coil, the compass needle would deflect towards east and west. Such instruments were useful in their time, but have little place in the modern world except as proofs of concept and elementary experimental devices. They are highly susceptible to motion of any kind and to any kind of disturbance of the natural field of the Earth. Nowadays, the term galvanometer usually refers to any design of electromagnetic meter movement built for exceptional sensitivity. Practical electromagnetic meter movements can be made now where a pivoting wire coil is suspended in a strong magnetic field, shielded from the majority of outside influences. Such an instrument design is generally known as a permanent magnet moving coil, or PMMC movement. In this picture, the meter movement needle is pointing somewhere around 35% of full scale, 0 being full to the left of the arc and full scale being completely to the right of the arc. An increase in measured current will drive the needle to point further to the right, and a decrease will cause the needle to drop back towards its resting point on the left. The arc on the meter display is labeled with numbers to indicate the value of the quantity being measured, whatever that quantity is. In other words, if it takes 100 microamperes of current to drive the needle fully to the right, making this a 100 microamp full-scale movement, the scale would have 0 microamps written at the very left and 100 microamps at the very right, 50 microamps being marked in the middle of the scale. In a practical meter, the scale would be divided into smaller graduating marks, probably every 5 or 1 microampere, to allow whoever is viewing the movement to infer a precise reading from the meter's position. The meter movement will have connection terminals for current to enter and exit. Most meter movements are polarity sensitive, one direction of current driving the needle to the right and the other driving it to the left. Some meter movements have a needle that is spring-centered in the middle of the scale sweep, instead of to the left, thus enabling measurement of either polarity. Common polarity-sensitive movements include the Weston and D'Arsavinal designs, both PMMC-type instruments. Current in one direction through the wire will produce a clockwise torque on the needle mechanism, while current on the other direction will produce a counterclockwise torque. Some meter movements are polarity insensitive, relying on the attraction of an unmagnetized moving iron vane towards a stationary current-carrying wire to deflect the needle. Such meters are ideally suited for the measurement of alternating current, or AC. A polarity-sensitive movement would just vibrate back and forth uselessly if connected to a source of AC. While most mechanical meter movements are based on electromagnetism, electron flow through a conductor creating a perpendicular magnetic field, a few are based on electrostatics, that is, the attractive or repulsive force generated by electric charges across space. This is the same phenomenon exhibited by certain materials, such as a charged balloon with popcorn stuck to it, when rubbed together. If a voltage is applied between the two conductive surfaces across an air gap, there will be a physical force attracting or repelling the two surfaces together, capable of moving some kind of indicating mechanism. That physical force is directly proportional to the voltage applied between the plates, and inversely proportional to the square of the distance between the plates. The force is also irrespective of polarity, making this a polarity-insensitive type of meter movement. Unfortunately, the force generated by the electrostatic attraction and repulsion is very small for common voltages. In fact, it is so small that such meter movement designs are impractical for use in general test instruments. Typically, electrostatic meter movements are used for measuring very high voltages, many thousands of volts. One great advantage of the electrostatic meter movement, however, is the fact that it has extremely high resistance, whereas electromagnetic movements, which depend on the flow of electrons through the wire to generate a magnetic field, are much lower in resistance. As we will see in greater detail to come, greater resistance resulting in less current drawn from the circuit under test makes for a better voltmeter. A much more common application of electrostatic voltage measurement is seen in a device known as the cathode ray tube, or CRT. These are special glass tubes, very similar to television view screen tubes. In the cathode ray tube, a beam of electrons traveling in a vacuum is deflected from its course by a voltage between pairs of metal plates on either side of the beam. Because electrons are negatively charged, they tend to be repelled by the negative plate and attracted to the positive plate. A reversal of voltage polarity across the two plates will result in a deflection of the electron beam in the opposite direction, making this type of meter movement polarity sensitive. The electrons have much less mass than metal plates and are moved by this electrostatic force very quickly and readily. Their deflected path can be traced as the electrons impinge on the glass end of the tube, where a coating of phosphorus chemical emits a glow of light seen on the outside of the tube. The greater the voltage between the deflection plates, the greater the electron beam will be bent from its straight path, and further the glowing spot will be seen from the center of the end of the tube. This principle is used in the oscilloscope for measuring changing voltages. An oscilloscope is able to draw a graph of a changing voltage. It can show a graph of a voltage or signal that changes far too fast for a meter to register.